So it's a great privilege, honor, and happiness for me to interview Professor Michel Revelle, a member of the Israeli Academy of Sciences. And I'm honored that you asked me, your son, to help with this interview. And I'm really proud and happy that we celebrated your 80th birthday. And we're going to try to tell your story from different angles. As a member of the family, I, of course, represent all of the family in our joy of your achievements and also all the happiness that you bring to so many people. So first, I'm very curious to learn what brought you to medicine. Why did you choose this field?
Yeah, as you know, I was born in Strasbourg, in France, in 1938, and my father was a physician. He always told us, we are three brothers, he always told us that he wanted to be a scientist and a researcher, but he didn't have the means, the money to do that, and he had to work as a physician to earn his living. But I think his passion for science actually influenced us. My two brothers are scientists as well. My older brother is at the California Institute of Technology in biology, and another brother is at the Weizmann Institute in physics. So I was supposed to be the physician of the family, but I also wanted to do research. So actually, at the University of Strasbourg, I was one of the first students to do an MD PhD program, to work in a laboratory at the same time, and I could learn medicine, but actually I wanted to be in medical research rather than in medical practice.
So your father, as a being, he was a otorhinolaryngologist, ears, nose, and throat specialist. But also, I know that during the war, during the Second World War, he was occupied in other issues.
My father was very deeply involved in Jewish congregation and work for the Jewish people. During the war, he was very active in what is called in French the Organisation Secours aux Enfants, the organizations that helped Jewish children to escape the Shoah, and particularly in Lyon, where we were during the war. He was very active in hiding children in monasteries or churches, was very close to the church, to the bishop of the church in Lyon. But then in 1942 we had to hide from the Germans who had invaded the south of France as well. And he took us to the Alps. And in the Alps he was in the Maquis, the underground, the free forces, French free forces, and he was a physician in a hospital that was on top of a mountain. So my father was really a person who was very active socially and medically, and he worked very much for the good of the Jewish people. And I think part of our Zionism really taught us to be Zionists, and that, of course, brought us eventually to Israel.
So we spoke about your father. I called him Abbé, Gaston. And can you tell us a little about your mom?
My mom, my mother was from a small town next to Strasbourg called Obernai, and she was very active also in social work, in the congregation of Strasbourg. And her brother is a very famous French philosopher and rabbi Professor André Neher, who founded the first cathedra, the first department of Jewish study at the University of Strasbourg. There was no such thing in France, and he was a pioneer. He also was a leader who taught us about Jewish identity, and in his many books, he wrote some 20 books, he carried the message of humanism, of Jewishness being actually a lesson in humanism and care for the other. He wrote about prophets, he wrote about the Shoah, and also we were very influenced by him to come to Israel. Actually, in Strasbourg, I also met Claire, my wife, your mother. We went to school, to the Jewish school together, and from there, from the age of 16, we are together. We may come back to it later.
So, growing up during the war, many years you did not attend school.
Yeah, that's right, but I was very small. I was before school years during the war, and when we came back in 1944 to Lyon, then I started to go to school, and later on we moved back to Strasbourg, which is in the east part of France, and I did most of my studies in Strasbourg until the university.
And you attended the university in Strasbourg, and you did your thesis there.
Yeah, so I did both medical school, but I was not a very good student, as I said, because I was more interested in research. I had the chance from the age of 18 to work in the laboratory of Professor Paul Mandel, who was head of the biochemistry department, professor of biochemistry, and he took me in his lab. So I was working in the lab studying medicine and also studying for the PhD in his laboratory. So I did my PhD with him, and eventually in 1963 I obtained my MD and PhD, and Claire obtained her doctorate in physics, biophysics. So we were very active, very busy, and you were born in 1961, so we started everything, science, life, family. That was an exciting period. And then we went for postdoctoral fellowship at Harvard. I had the chance to be in the laboratory of Professor Howard Hyatt. He was the chief of medicine of the Beth Israel Hospital in Boston, and he was a student of Jim Watson, and also a very good friend of François Gros, Professor François Gros from the Pasteur Institute. We'll speak about him later. So I had this 1 year of postdoc at Harvard, and of course I was supposed to continue for a second year of postdoc, and was even offered a position at Harvard, but we very much wanted to be in Israel. So I met by chance during one of the conference at Harvard, Professor Uriel Littauer from the Weizmann Institute of Science, and I told him that I wanted to come to Israel. He said, why not you do another postdoc in Israel? So after 1.5 years in Boston, where your brother was born also, Sami, we went to Israel, and we had 1 year at the Weizmann Institute of Science in Professor Littauer's biochemistry department.
So was there a scientific relation between what you did in Strasbourg, at Harvard, and at the Weizmann, or every time it's a different topic?
You will be surprised that in Strasbourg, when I was studying biochemistry, biology, this was before the DNA era. We had professors who said things like there is no relation between nucleic acid and protein. This is just an idea. But fortunately, my mentor, my thesis director, Professor Paul Mandel, he already was a molecular biologist. He understood the importance of molecular biology. So I worked on RNA, I worked on the synthesis of RNA and of proteins. And when I came to the United States for my postdoc, I was given a project on liver protein synthesis. And so there was a relation between the two. We actually showed that liver cells do not divide and that proteins are made, because everybody has this model of bacteria where the cell divides and produces protein at the same time. But in human organs, very often there is no cell division, but still messenger RNA is producing proteins. And the surprise, actually, this was one of the findings, my first finding of importance, was the stability of the messenger RNA in liver cells as compared to cells that replicate and divide quickly.
So there was some gap between the scientific approach in France versus United States at the time?
There was a big gap, first of all, of language, because in France, most of the scientists did not speak English. They didn't read very well the scientific literature. They wrote their articles in French. So coming to the US and being in one of the biggest universities in the world, I really had a big change. Fortunately, my older brother, Jean-Paul Revel, was at that time also at Harvard. He was a professor of anatomy, which we would say is more histology. Actually, he was an electron microscopist. And he helped me very much to adapt to the new science and the high level of science that was, of course, in the United States. And when we came to the Weizmann Institute, also we felt this big difference with the old continent, with the French and European, German culture, because here everything also at the Weizmann Institute was in English, the lecture was in English, the teaching was in English, so they understood the importance of being part of this new science. And I was working also on molecular biology, on transfer RNA for a year with Uriel Litauer. And then at the end of this year, this was 1964, I had to go back to France to do my military duties. Because as a young student, before starting medicine, which is 7 years in France, I obtained a deferment from the army. But if I would not come back and honor this deferment, because you take the engagement, you take the responsibility of coming back and doing your military studies, military duties after the university. So I had to come back in 1964, and we chose to live in Paris. And very fortunately, instead of being a physician in the French army for taking care of, the personnel, the families of the personnel, which is not very interesting, I managed, with the help of my father and his relation, to be sent to a laboratory, to a research laboratory. And my great chance was to be sent to the laboratory of Professor François Gros, who was in Paris. Later on, he was the director of the Pasteur Institute. And from him, who again was a student of Jim Watson, I learned most of the molecular biology.
Why would the army be interested in you doing this?
Well, this was not so simple. Actually, was sent to a laboratory in a hospital in Paris, the Val-de-Grâce, a big hospital, and was supposed to be with one of the researcher who was there. But this researcher, for some reason, wanted to please François Gros, and he said, okay, although you are officially working in the Val de Grâce, you can go to the laboratory of François Gros and you can work there. So that's why
you didn't have to wear a uniform.
I didn't have to wear a uniform, but I had to go every 15 days, every 2 weeks, to the office at the hospital, the Val de Grâce, and take the pay of the French soldier, which was nothing, as cigarettes. Yeah, and I said, I don't smoke. I said, you have to. I mean, this is a part of what... At the time in France, actually, they, because of the taxes, they actually encouraged young soldiers to smoke. So that's another story.
What brand this was?
Troop. The cigarette, they were called a troop. Troop means army in France. So everything was organized. But
so they actually paid doctors by cigarettes and told them that it's good.
Yeah, this was in 1964, 65. And things have changed now. I don't think the French do that anymore.
So in Paris, my brother Amos, Zichrono Livracha, and Shoshana, my younger sister, were born.
That's right. We had 2 more children, and Amos, you said already, he passed away after his military service in Israel, after serving in Tzal, during one of those trips, post-army trips to South America. He died on Machu Picchu in Peru. He drowned in an accident, and at the age of 22, he died. But your sister, Shoshana, now she's Professor Shoshana Wilk. She's a physician also, as you are. And I'm very proud of all of you, and also of Sami, who is an ambassador to Cyprus. So we are very proud of our family and all the grandchildren that were born from your marriage.
So as we manage to talk about Amos, my brother, maybe we can mention that after his death you found some stories and some pictures.
Yeah, he died just after we had been for 1 year of postdoctoral, sabbatical, sorry, in New York. This was one of the many sabbaticals that we took, and I saw him always, writing or drawing, and we found many pictures that he had made and poems that he wrote, and in his book, this book called Velo Echdal, we put together these poems and these drawings, and I think it's good to have something from him that remains and that we can distribute to the family. He was very gifted in writing poems, and had he lived, I think he would be a writer, because that really was his quality. He was also a very charming person, an artist, and it's a pity that we lost him.
And he is named Amos after a book written by André Neher that you mentioned before.
Right. André Neher, in one of his books on prophets, he wrote a book about Amos, and this was the reason we called our third son after this book, and also because André Neher did not have children. So we thought appropriate to call it after this book.
So now you just finished your army, like Israeli youngsters finish at 21 or 22. But when you finish the army, you have 4 children, you have MD, you have PhD. you're married, you're in Paris, you have a position at the Institut Pasteur. So why aren't we in France anymore?
Yeah, and we enjoyed very much the work with François Gros. There, I think I made a significant discovery of the initiation factors of protein synthesis. This actually was in 1966, and it taught us for the first time how ribosomes are finding the place to start to read the genetic message. Because we knew that RNA is a sequence of nucleotides, and you have to, it was after the discovery of the genetic code, of course, by Crick and Watson, and it was difficult to understand how the ribosome knows where to start, because if you start at the wrong place, you won't be able to make the protein. And the initiation factors are proteins, which there are 3 of them in bacteria and more in mammalian cell, and they are indicating to the ribosome where to start, and also bringing the first tRNA to initiate the synthesis of the protein. So I enjoyed very much the work in the laboratory of François Gros. He was a wonderful molecular biologist, geneticist, and
you went to his birthday recently.
Yeah, he was 90 years old 2 years ago, and he's still active at the French Academy of Science. He was actually the secretary perpetuel, that is, immortal secretary of the Academy of Science, but now he is retired. So we enjoyed very much our time in France, and especially in the laboratory. We had also the 1968 French students' uprising, so we had plenty of ideology and plenty of ideas of making the world better.
So you participated in the riots?
Not in the riots, but in trying, in some of the marches, yes. Actually, I still remember going down the Boulevard Saint-Michel in Paris, passing the Sorbonne, which is a Paris university, and the bells were ringing, and we chanted the International. This was not a communist, but there was something universal that the students really were realizing that they were human beings, that there was a world, that there was a responsibility for this world. And at that time, I think it was very enthusiastic, and we enjoyed being in this society. But you are right. What happened with our dream to live in Israel? And in 1967, there was a war. And suddenly we realized that almost we were traitors, because instead of coming to Israel, we were enjoying life in Paris. After the army, I had a position at the CNRS, and I had a good pay. So we immediately decided that now it's time to immigrate, to make Aliyah to Israel.
During the war?
Yeah, the first day of the war, I was supposed to give actually a talk at the French Jewish congregation on some question of science and religion. And we heard about the start of the Six-Day War and went immediately to the Israeli embassy in Paris, say we want to come to Israel. I said, did you go to Tzal? Did you go to the army? I said, no, I'm just, a French army. You learn almost nothing about fighting. So they said, so go home and go through the
We don't need you.
Go through the Jewish agency, and if you want to come to Israel. It took us another year, and in August 1968 we made Aliyah with all our 4 children, and you were the oldest one. And fortunately we had a position at the Weizmann Institute, and it was already a permanent position, Kavua, so we could make the jump, and I started to work at the Weizmann Institute in the Department of Biochemistry, and most of my career I did then at the Weizmann Institute.
Yes, but they made you repeat the army service in Israel.
Yeah, I had a short period of 3 months where I was in the army, and then I learned how to use weapons and how to fight a little bit.
But I remember you told me once a story that you were put in patrol to be a guard.
Yeah, this was in 1973 already, in the Yom Kippur War, because I had not told the Israeli army that I was a physician. I was actually a professor at the Weizmann Institute. They did not ask more questions. But in 1973, I was put on patrol on what's called Chel Kshishim, the army of the old people, to guard different facilities of the army. And I said, no, I'm still too young to be just guarding facilities. And I told them, you know, I have an MD. So the next day I was sent to the medical corps at Tel HaShomer, and since I was working on interferon, they put me in writing a book about how to fight viral attacks using interferon. Okay, so it was very unreal, because at that time interferon was still only a subject of scientific research, nothing that could be used in humans. But it gave me the possibility to do something for the medical corps of Tzahal. Mm-hmm. Yeah.
So you wrote a book on?
Wrote a little booklet, yeah, on defense against viral infection, viral attacks. Still a very big problem today,
yes,
as we know.
So it's not used in chemical warfare or in biological warfare.
No.
But it has maybe it's a time to say a little what interferon is.
Yeah.
Since
why I started to work on it.
Why did you find this interesting?
So the first few years at the Weizmann Institute, the first 2 years, I continued to work on initiation of protein synthesis in bacteria, in mammalian cells. We discovered also the initiation factors of the mammalian cell. I started to work on that. Today it's a big field, but we were at the beginning of this research. And also I met Professor Ada Yonat, who used to come to my laboratory when she was younger. And she was very interested, of course, in ribosomes and in initiation factors. And she wanted me to produce these proteins so that she could crystallize them and do their structure. And she even now, after receiving the Nobel Prize, always recalls that she was very interested in what we were doing. Actually, she showed that our hypothesis about the function of the initiation factor to let the ribosome recognize the first codon of a message, which is AUG, she showed by crystallography that that's what one of these proteins is doing. So this was very exciting, very interesting, although it was much before she was able to crystallize ribosomes. And I suddenly remembered that I was a physician, and I said I must find some medical application to what we are doing. By chance, I met at one of the EMBO courses Argentinian scientist who was working in Paris, Ernesto Falkov and his wife Rebecca Falkov, and they were working on interferon. And at that time, nobody knew very much about interferon, which had been discovered quite a a while before by Lindman and Isaac. The only thing which was known is that if you take cells or even an egg and you infect it with viruses, one virus, and then you try to infect it with another virus, the second virus will not grow. Okay. So that's the name interferon. It interferes with the second virus. But interferon was sort of a myth. The protein was very difficult to, there was very little protein made. Nobody could isolate it. Many people didn't believe it was really a protein. And nobody had an idea of how it worked. So in 1970, with the help of Ernesto Falkov, we set up in the laboratory at the Weizmann the production of interferon, and we started to do some molecular biology. And the idea was the following, that we knew that many viruses have RNA as their genetic component, and that the protein of the virus are not made in the cells that have seen interferon. So we asked, if it's RNA, it means that the ribosome can, for some reason, not start to read the message or not able to produce the protein. And that's why, because coming from the field of initiation of protein synthesis, I said this may be a very good system. It has to do with viruses, with disease, with flu, with other viruses. Poliomyelitis is also an RNA virus. Maybe we can do something. And we started to work, and in the next 3 to 4 years, we were one of the 3 groups in the world to elucidate the mechanism of action of interferon, how it blocks the ribosome from starting the message, how it can degrade the messenger RNA, which is very interesting. And
so it has an effect both on the transcription and on the messenger.
Yeah, if you look at DNA viruses, it can have an effect on transcription. But if you look at RNA viruses, then the effect is mainly on the stability of the message or on the initiation and the synthesis of the protein.
So there is 2 different mechanisms?
Interferon has many mechanisms of action, and actually we were the first in my laboratory to clone genes that are induced by interferon. That is, when interferon works, it acts through a receptor, which actually worked also later. This receptor activates a number of other genes. And among these genes is a ribonuclease, which is activated by double-stranded RNA. So actually the genomic part of the virus is activating this ribonuclease. There is a protein kinase, which is blocking the initiation of protein synthesis. And that also was some work we did with Professor Ray Kempfer at the Hebrew University, who I had met before at Harvard, so we were friends. So interferon has many mechanisms of action by this number of genes that I think today we know of more than 20 genes which are activated by interferon. So it's like a hormone, like a cytokine that activates the formation of these protein, and this protein mediate the different effects on transcription, translation, and also an assembly of virus, because interferon can also act on that part.
So what you're saying actually is that sometimes you remember that you are a physician. If you're in the army and put as a guard, you remember that you are a physician. And if you're at the Weizmann and there is so many people doing the basic research, then you remember that you're also a physician and you have to look for a cure for something.
Yeah, I think it's all related to the fact that my father sent me to medical school to be a physician. Maybe I disappointed him. But the fact that I studied medicine made a big difference because you look at science in another way. And I think when you are interested in medical application, you understand, you see it from the patient point of view, from the disease point of view. And interferon turned out to be much more varied than we thought at the beginning. And you know, I'm speaking now for the scientific community because there were hundreds of people at congresses on interferon. It was a big field in the 1970s. And one of the effects of interferon is also on the immunomodulation. And there we had 1 year the visit of Professor Mark Fellows, that you know also.
Yes, I remember.
The geneticist in Paris. And he took several months in my laboratory at the Weizmann Institute. His specialty was HLA, the histocompatibility genes. And we were first to show with him that interferon can inhibit the formation of HLA proteins and can make modification in the immune response, reduce the immune response, and immunomodulatory activity.
So you switched from the biochemistry part of initiation of transcription of genes to looking for a cure for viruses, and now you switch to the immune part, so looking at the role of interferon on immune modulation.
We were following the story of interferon and its many different actions. So it has an anti-proliferative action, that is, at some time maybe it could have activity in cancer. So it seemed to have a lot of possibilities to apply interferon in medicine. But there was no source of interferon because, as I said before, it was made in very tiny amount by cells. And we decided that in order to continue, we have to set up a production of interferon on a larger scale. And then, again, it's with the collaboration with Jan Wilczek, Professor Jan Wilczek from NYU, we started to work on diploid human fibroblasts. Those are cells that can be not cancer cells, they can be cultured in large amounts, and they produce interferon if you treat them with something which looks like a virus, a double-stranded RNA. And we decided to make a big collection of these fibroblasts. Where can you get fibroblasts? We thought the easiest is to take the Brit Milah, what you cut during the circumcision, and
supposed to be buried.
Yeah, the foreskin cells, supposed to be buried, but fortunately we got permission from a very famous rabbi, the Rabbi of Lubavitch, because his niece was working in my laboratory, so she did not hesitate. She wrote him a letter, and we got, a letter that then we showed to rabbis, and they let us come to circumcision with a petri dish, and they could put the foreskin in the petri dish instead of putting it in the earth. And we grew these cells, and we compared actually different children, if you can say, or donors, and we found that some of them had a lot of interferon and some much less. So we had actually a possibility to choose those that make a lot of interferon, to grow them in large amounts, relatively large amounts in my laboratory at the Weizmann Institute, and to make a production of interferon. Then
has anybody else tried to use the foreskin for anything else, or this was just your idea?
It was, yeah, I said the idea came from Jan Wilczek, who had made one line like that. But I think we were the first who made a big comparison, because we could access to foreskin of many different children and see this variation. I still regret today not having done the genetics of these people. Probably we would have found, but it was before the time when one could do DNA sequencing and isolate genes. It was still in the 70s. So the Weizmann Institute is a place of basic science. And when I came to Michael Sella, who was then the president of the Weizmann Institute, he said, I can help you having a bigger laboratory, but I don't want you to do industrial work or to do something on a large scale. For that, you must find a company, an industrial company, pharmaceutical company, that will be interested in your project. So with the help of Aaron Metal, Dr. Aaron Metal, who was at the time the director of YEDA. YEDA is the arm of the Weizmann Institute dealing with technology transfer. We started to look for companies. We decided that we want to have a partner that will open a company in Israel. Not a company in the United States or in France, but in Israel. And that he will undertake that if we can produce interferon in large amounts, there will be a plant in Israel producing at least half of in Israel and maybe the other half abroad.
When I made a film for, I think it was your 70th birthday, I met Professor Mirelman. And he told me the story from a little different angle, if you remember. He said that actually this guy came from Italy, and he said, you know, there's wise people at the Weizmann Institute and in Israel in general. I want to invest in something. And they found you.
Yeah, after looking for many companies, one day, at the end of '79, Mr. Fabio Bertarelli, of blessed memory, came to the Weizmann Institute. Actually, it was not the first time he did something in Israel, because he had worked with Professor Bruno Lunenfeld, and he had made Pergonal, so that's very close to your field. The first medication for
this was made from
in vitro
menopausal women.
Right, it was isolated from urine of menopausal women, a few nuns, I believe, in Italy. And so he had already made Pergonal. It was a main drug used in vitro fertilization at that time. So he knew Israel, and I think because of that he came to the Weizmann, and he was interested in the interferon story.
Company.
Yes, Serono company. They just moved from Rome to Geneva. They wanted to become a big Swiss pharmaceutical company, which they did. And they wanted to do something more than Pergonal. And he chose to do this project on interferon. Actually,
but at the time, you did not know what the application would be. You were just manufacturing something.
As I said, we thought maybe against viruses, maybe against...
but how do you produce something that you don't know what it's going to be used for?
We knew it would have some medical application, and the whole world was looking for it. Even some people said the magic bullet, you know, it will cure many diseases, but that was not the case. But still, one must say that there are different types of interferon alpha and interferon beta. Interferon alpha, there are many genes, and the interferon is found in the blood only. It's made by blood cells. And interferon beta is the only one made by all cells of the body, skin, organs, brain, what have you. So we chose to work on interferon beta for that reason, because it seemed to us more general. And we started to produce from our foreskins culture, industrial production in a building next to the Weizmann Institute, actually in the Science Park of the Weizmann Institute, the Weizmann Park. The company was called Interpharm, and there we started to produce the foreskin cell in large quantities, extract the interferon, and this was instrumental eventually in doing the cloning of the gene for interferon, because we knew from the beginning, and it actually was part of the program I presented to Mr. Bertarelli, that we would first start with natural interferon beta, but then we would try to isolate the gene, and since genetic engineering started late in the 70s, we wanted to isolate the messenger RNA, use the reverse transcriptase to make the cDNA and clone this gene, and then produce it by genetic engineering. Yes, you can say we had plans to produce something and we didn't know how to use it. Not only that, but I had a conference in 1978 on interferon at the Weizmann Institute. And there was a Belgian professor who came and he said interferon beta will never be applicable in medicine. Because when you inject it, and he had done that in humans, you don't find it in the blood. While interferon alpha, you find good levels of interferon in the blood. So he said, you should abandon interferon beta, it's not going to be useful.
But you're already producing it, so you must find some application for it.
No. I probably would have abandoned it if I had not met an Italian friend who told me that he had done experiments and he found that the interferon beta was in the lymph system. And it's very interesting. Interferon beta is a glycoprotein, it has sugars, and when you inject it, it goes into the lymph system. But still, we had to prove that interferon, if you inject it, you are going to have a response of the human body, otherwise really we should abandon it. And then we made use of the fact that we had all these genes induced by interferon. We had probes that we could use to see if when we inject interferon to a volunteer, to a human subject, we would find that his blood cells have activated these genes. And I was fortunate then to, just by chance, came a young MD student from Kaplan, Shatner, Amichai Shatner. He was later on professor in the internal department at Kaplan Hospital in Rehovot. And he made these basic science studies exactly on that idea. And he was able to prove that even if you inject interferon beta in the skin and you don't find it in the blood cells and other tissues of the body react by inducing these genes and making the RNA and proteins of these genes. And that actually was a proof that we needed to continue our project. I think it was an important contribution, because otherwise maybe interferon beta would not be used medically.
So what came first, the application or the switch to the recombinant manufacture?
We started with application, and actually we used the natural interferon with glycoprotein, which we could purify in some way to treat disease like herpes. Actually, we made a cream of the natural interferon. It was called Fron by Mr. Bertarelli, by Serrano. Fron, and it was very active against genital herpes. Actually, it's the only topical treatment of genital herpes that reduces the recurrences.
So how does it work?
It's not, they didn't want to continue to work on that. They said, cream, it's too cheap, it's not going to be good enough. And then there was also some new drugs, acyclovir, that came up. So, although I still believe that herpes was a very good choice, we also used it as drops in the eye at Tel HaShomer Hospital. We had some work and some publication that it prevented adenovirus conjunctivitis. So it has clear antiviral activity. But they were looking for something bigger, a bigger indication. And
so Fron was made from the natural product.
It was a natural product made from foreskin cell. And there was another application in condyloma. And actually we worked with Dr. Bornstein, and we had some nice results on condyloma, which is a papillovirus. Yes. So it has applications, but for example, interferon alpha is used in hepatitis C, not alone, but in combination, and it's still used today. But interferon beta did not make it to hepatitis. So we had a brainstorm meeting in Rome, in Italy, and I just edited a book about interferon and clinical applications of interferon. And I'd invited one researcher from Buffalo in New York who had started work on multiple sclerosis. And since we had done this work on immunomodulation, and other people had shown that immunomodulation was a very important role of interferon, we said, that's an unmet need. Multiple sclerosis is a disease in which really there was no treatment at the time. It was before Copaxone and before Rebif. And we decided that this was the disease we would try to work on. But for that we needed large amounts of interferon, and we were doing the cloning of the gene. In 1980, at the end of 1980, we had isolated the human gene from the human genome. This was one of the first human gene which could be isolated. I say that because interferon beta gene does not have introns. So you can use the gene itself to produce a protein. You don't need to use the cDNA. And that was very interesting. And
only exons.
There's only exon. So you can use the gene, you can isolate the gene from the genomic DNA. Without going through cDNA, you can introduce it into mammalian cell with an appropriate promoter. And in 1984, we had a cell line of Chinese hamster ovary cells, so a mammalian cell line, which was producing very large amounts of interferon, secreting it constitutively. You didn't need a virus or anything to induce a cell to produce interferon. It was constitutive because we had put the right genetic promoter in front of the gene, and it produced the glycoprotein. Because
like the natural?
Like the natural one. And actually all the studies which were made on the structure of the sugar showed that it was 99% similar to the natural sugar. So in 1984 we had this method, we had a patent on the method, and even a couple of years ago about I had to testify in a trial. Another company, Biogen, tried to destroy our patent. It was from '84, so it was 20 years later. But eventually the court found that we had enough proof. Of course, there were prior work on bacteria, but when you put human genes in bacteria, they make protein without the sugar. Mm-hmm. And the fact that we could produce in mammalian cell for the first time with a sugar, a molecule which is almost like the natural protein, allowed to go forward and to use it really in medicine. So
in 1984 you have production of the interferon, and it's very similar to the natural.
That's right. So it had to be upscaled, and that again was done at Interpharm. We started with 5 liters, and then 10 liters, and 75-liter bioreactor. And today it's produced, unfortunately no more in Rehovot, but in Vevey, on the Lake of Geneva, in fermenters that are 3,000 liters bioreactors. So the production could be now enough to treat thousands of patients, hundreds of thousands of patients in the world. And
using the same method?
Using the same method, the same type of cell that we had produced in 1983-84 at the Weizmann Institute. So Serono made many clinical trials on multiple sclerosis, demonstrated its activity, and the drug was approved for market in 1998 in Europe, in 2002 in the United States. In Israel, it was always compared to Copaxone, which came also at the Weizmann Institute. So it's very interesting. The Weizmann Institute produced 2 drugs against multiple sclerosis. But those drugs are still used today, although there are new drugs coming up, but they are the safest and the best drugs for multiple sclerosis.
But the mechanism of work is very different.
Absolutely. What interferon does is to reduce the activity of the immune system, and maybe we can just explain it. When there is a viral infection, the first thing the body does is to produce interferon, which blocks the virus as much as it can. Then the body produces antibodies. There's an immune response. But when there is an immune response, there is always a danger that the immune response will be too strong and that it will cause autoimmune disease. And multiple sclerosis is an autoimmune disease in which the immune system attacks normal tissues. And then interferon has a second function to modulate, to quiet down the immune system so that it will not go overboard. So I think it's very logical from the biological point of view. A virus comes in, first you get interferon, you get the immune system activated, and in order for the immune system not to be too strongly activated, you need again the interferon. Mm-hmm. And having this scheme in mind, we saw that multiple sclerosis was really a good choice because it's an autoimmune disease. When T cells, which recognize, of course, some autoantibodies enter the brain, and that, of course, is an accidental event, can be due to trauma, to virus infection, but once these cells are in the brain, they attack the cells that produce the myelin sheet along the nerve. Those cells are called oligodendrocytes. And an attack of multiple sclerosis is starting, because the type of multiple sclerosis we were interested in is called relapsing remitting multiple sclerosis. There are attacks, the relapse, and then it quiets down again, and there is a remission, but then there will be another attack. It can be 4 or 5 attacks like that during a year, and every time the patient will lose some neurological activity. So it can affect the movement of the hand or the walking, sometimes even the brain, and the importance is to reduce the number of the attacks and to prevent the neurological deterioration. And I must say, we don't have time to go over all the clinical trials. I'll just give you 2 pieces of information. In 2016, that is 2 years ago, 2.5 years ago, there was a meeting in Berlin for the 20th anniversary of Rebif. And what was fascinating is that the neurologists, 300 neurologists who were there, in majority they were using Rebif for 15 years or more. Rebif is a commercial name of interferon beta. It's not Revel beta interferon, but it's recombinant beta interferon. So they could say results of treating 10 or 15 years patients. And the overall outcome is that 86% of the patients who were treated for 15 years with interferon beta, with Rebif, they did not need any help in walking. They did not need a cane, they did not need braces, or of course not a wheelchair. They could walk by their own. And that's 86% of the patients treated. Of course, you have to start early in the treatment, before this paralysis develops. And 80%...
And they need to continually be on.
It's a treatment 3 times a week, subcutaneous injection. Serono developed a special syringe which is filled with a drug already, so the only thing the patient has to do is to take the syringe and apply it to the muscle, and automatically it injects, like the atropine syringe that the army is using. So it's very simple for the patient. But it's still,
or for the company,
it's not as easy as taking a pill, but it's relatively easy. And patients have a good compliance, and for 10, 15 years can be treated. So the second result was that 80% of the patients treated for 10 years, in that case, did not progress to secondary progressive multiple sclerosis, because that's one of the big danger, that after you have this relapsing remitting phase with inflammation and entry of T cell in the brain, there can be progressive disease. That is, the neurons are dying by themselves and now unrelated to the myelin loss, and you want to prevent that. So if you can do it in 80% of the patients, it's not perfect, but it's certainly a big achievement. There are 2 companies in the world producing the recombinant interferon from Chinese hamster ovary cell. One is Serono, which is now Merck since 2006. The Merck in Germany, Darmstadt, have bought Serono for $6 billion, and they, in which 60% of the revenue were from Rebif. So you can see that it was a big operation. And they continue now to commercialize Rebif for MS over the world. And the second company is Biogen, a very large and famous company in Cambridge, and they use the same procedure, so they are covered by the same patent from the Weizmann Institute. So together, I think we have about more than 500,000 patients treated. The sale
all by the original method.
Yes, and the sales are together over $5 billion a year of sales of Rebif. So it has become a drug which is well accepted in the treatment of multiple sclerosis, and it has allowed also the Weizmann Institute to receive royalties and to make the biotechnology in Israel one of its achievements. Of course, there are several achievements, but this is one of them. And actually, when last year, for the 70th anniversary of the State of Israel, they issued a book on the discoveries. Innovation, exactly. So, Rebif is one of them. Mm-hmm. And I was very proud that they included it in the innovation of the...
So it's cited as maybe one of the pioneers of biotechnology in Israel and worldwide.
Yes. But of course, biotechnology in Israel is very, very dear to me. I was chairman of the Biotechnology National Committee for several years, and I tried to develop biotechnology. And I regret that Interpharm was closed because Serono was sold to Merck in Germany. But when I speak today with the people of Merck, they say, why did they close? We would have loved to have a company in Israel. So there were some misunderstanding, problems of taxes also. I don't want to go into at the time of this sale, because, you know, in Switzerland, they understand the importance of biotechnology and they can waive the taxes, zero taxes. But in Israel, they wanted to have, government wanted to have some revenue, and they did not accept to reduce the taxes enough, and this was part of the reason this company was closed.
But in a way that's good, because that forced you to move to something else.
Yeah, you can say. And I must say also that biotechnology in Israel has developed, and there are many companies that are working today. So some succeed less, some succeed more. I wanted to have something to do with the biotechnology, and I was reaching the age of retirement at the Weizmann Institute. Although I must say that during the years from 1980 to almost my retirement in about 2006 or 7, we had grants from Serono, which helped us to do a lot of research. We discovered interleukin-6. We worked a lot on this cytokine, which is very important for many immunomodulatory activities and also for the liver. And every day there are new discoveries about interleukin-6. It has some role in neuropathies. One can use it to treat chemotherapy-induced neuropathies or diabetes-induced neuropathies. So we continued our research. And
you made a chimera. I remember you explained to me a chimera of IL-6.
Yes, because IL-6 can work through a receptor which has two chains. One chain is actually inside the membrane, and the other chain is partly in the membrane, but can also be soluble, secreted. And together with my colleague, Professor Menachem Rubinstein, and Daniela Novik at the Weizmann Institute in my department, in the Department of Biochemistry, it was after called Virology and then called Molecular Genetics. We found that this soluble receptor of IL-6 actually is a cofactor for IL-6. So if you present the cell with a mixture of this soluble IL-6 receptor and IL-6 itself, the ligand, they activate the second part of the receptor in the membrane much more actively and can do it in a large spectrum of cells. And we fused the two genetically to get a fused protein, and this helped us a lot in our studies. Unfortunately, it did not develop into a medical drug, at least not until today. Actually, from our group, Dr. David Wallach, Professor David Wallach, who was also part of the group, he developed a TNF binding protein, and this actually has become a very important drug for rheumatoid arthritis, Enbrel. But again, it was not made by an Israeli company. It was made, only the patent actually covered and brought some royalties to the Weizmann Institute. So this Serono investment at the Weizmann Institute of, we had very large grants of up to $600,000 or $700,000 a year. Together with my colleague, it was even more. So they had quite a number of products which were made. Some they used, some they didn't use. For example, Professor Zeli Geschrar, who was at that time a pioneer in the making the hybridoma and the monoclonal antibodies. But Serono decided that antibodies were not interesting. And so companies make big mistakes as well. We know the importance of monoclonal antibodies in treatment today. And they also missed the other discovery of Professor Zeli Geschrar. As I said, we come to the close of that collaboration after they sold Interpharm and were sold themselves to Merck. We thought to continue the work on multiple sclerosis, but in another way. We thought that if we could make the oligodendrocytes from stem cells, maybe we could have a way to have a cellular treatment to restore to the patient the ability to produce myelin. Because in multiple sclerosis, as I explained, because of the inflammation, the T cells, they destroy the oligodendrocyte, and then the myelin of the around the nerves is lost. And the idea was that maybe we can give back new oligodendrocytes to the patient, and so they can remyelinate the brain.
Because the treatment stops the disease, but does not rejuvenate the myelin sheet.
Exactly. So in 1998, there was a breakthrough in the stem cell field when they were able to isolate for the first time the inner mass of a blastocyst, of a human blastocyst, put it in culture and obtain embryonic stem cell culture. It was done in Madison, but in collaboration with Professor Yosef Itzkovich at the Technion, and very soon after Professor Benny Rubinoff, also in collaboration with a group in Australia, produced human embryonic stem cell. And we started to work with Professor Itzkovich, with Yosef Itzkovich, and very rapidly we were able to make good oligodendrocytes that myelinate in vivo. And if you inject them to an animal that doesn't have one of the myelin proteins, so it has no myelin in his brain, those mice are called shiverer mice because they are trembling. Not trembling because of cold, but trembling because of they don't have myelin around their nerves, and the nerve conduction is erratic. If you inject the cells, the oligodendrocyte we can make from human embryonic stem cell into the brain of these shiverer mouse, we got actually remyelination in the brain. And we did not have the patient to wait for a year or two, but some other researcher in California did that after us, and they waited long enough, and they could show that the animal works normally, that it can cure almost this genetic defect. So this oligodendrocyte gave us a lot of hope, but then we faced the difficulty, which is still today. How can you deliver them in the brain where there is demyelination? Because if the cells are well differentiated and are able to myelinate, to form the myelin sheet, they do not migrate in the brain. They stay where you put them. And if you take them very young, they migrate in the brain, but they don't develop because they are attacked again by the immune, other than the other. So we put multiple sclerosis aside. We said anyway there are drugs for it, and we thought of using a side product of our oligodendrocytes, which are the astrocytes, because when you differentiate human embryonic stem cell in ectoderm, and you go to nerve cells, to the nerve tubes, then you can get nerve stem cell. They can go in two ways: glial cell, which comprise oligodendrocytes or astrocytes, or they can go to nerves. So we could push them to become astrocytes. And we said, okay, astrocytes are very interesting drugs, very interesting cells for neurodegenerative disease, because astrocytes' their function is to protect the neurons, to prevent their death, because neurons are all the time producing neurotransmitters, for example, like glutamate, which, if it accumulates, will cause excitotoxicity, excite too much the neuron, and then because of that, the neuron will die. So the astrocyte takes up the glutamate, and in this way it protects neurons. In another example are free radicals, oxygen radicals. There also the astrocytes are removing them and preventing them from accumulate. In addition, astrocytes also secrete proteins, neurotrophic factors. So we thought that in neurodegenerative disease, it could have an application, and that's how we come to develop a treatment for ALS, or trying to develop a treatment for ALS, amyotrophic lateral sclerosis.
So this work was done first on funding from Serono because you were looking for other treatments for multiple sclerosis, and then moved to another project.
That's correct. And in 2010, actually, I finished working at the Weizmann Institute, and I decided to found a new biotechnology company called Kadima STEM with an entrepreneur, Mr. Yossi Ben Yosef, and I'm the chief scientist of the company. We are now more than 35 people working in the company. It's again located in the science park of the Weizmann Institute, and actually just across the road from Interpharm, so just across the street from Interpharm. And this park has developed a lot during this year. And Kadima STEM is now in clinical trial with this astrocyte produced from embryonic stem cells.
So you had already one patient?
Already one patient has been injected. At least we don't see big side effects. Of course, we cannot speak yet about efficacy.
But now it's not a systemic treatment. Now it's a treatment that is intrathecal.
Exactly. So the idea is to introduce human normal astrocytes in the cerebrospinal fluid, the CSF. We know that the astrocytes attach to the meningia and they stay there, and they can remove toxic compounds. They can produce neurotrophic factors. Actually, we have studied this neurotrophic factor. We have found that they produce quite a variety and also of antiproteases. And we think that in this way they will protect the neurons, the motor neurons, which are dying in the ALS disease. Mm-hmm. This has been shown in animal studies. We have done safety. And last year we obtained the authorization from the Ministry of Health and from the Helsinki committee of the hospital, the National Helsinki Committee, to start.
So this is a very big thing, that you can use stem cells for therapeutic indication and already moved to the step of clinical trials.
Yes, I think it has taken up about 6 or 7 years, but we got there. And not only we did the basic science, the preclinical, but the safety. We had, of course, input from the FDA, and we were able to obtain this authorization. Many people were skeptical because embryonic stem cells can produce tumors, teratoma, but we are not using embryonic stem cells as such. We are using them to we differentiate them into glial cell and eventually astrocyte in a long process. It takes more than 6 months. Then we can freeze down the cells at a precursor state, and we can use now these banks of cells that we have, just sow the ampule, grow it for about 2 weeks, and then they are ready for injection. Mm-hmm. So we are using actually differentiated cells, normal, healthy differentiated cells, and not the embryonic stem cells themselves. The embryonic stem cells are just the starting material, but the real product is what you obtain by differentiation. Mm-hmm. Now this differentiation, of course, is very complicated. It is guided by the genes which are activated. We want to make astrocytes which look like real human astrocytes, are healthy in the sense that they have all the properties which are lost by the astrocytes in the ALS patient. Because that is the main reason to use astrocytes is because in ALS patients, if you look at their astrocytes, they are not functioning well. They can even become toxic to the neurons. So we want to give to the patient healthy astrocytes that are actually able to fight the disease, hopefully. So that, yeah, is very happy that, after working at the Weizmann Institute, I now have a life at the Kadima STEM. We are a very young but enthusiastic company. We have another project in diabetes. There, again, we take the embryonic stem cell as a source material to differentiate pancreatic islets. Diabetes is a disease in which the cells that produce insulin in our pancreas are lost. They are actually destroyed by an autoimmune process in diabetes type 1, or they become less functional in diabetes type 2. And we have developed a procedure which takes 1 month to obtain functional islets that can be used for transplantation in diabetic animals. And in mice, we are able to reverse the hyperglycemia and to reduce the hyperglycemia to the normal level, to the normal glucose level in these animals. And now the big challenge is how to transplant these cells in humans. The FDA wants to have the cells encapsulated so that they can be retrieved from the patient. So we are working on different ways of wrapping the cell into different type of containers.
So this would be preventing attack by the immune system.
Yeah, you're absolutely right. One of the important role of the encapsulation will be to prevent the immune system from reaching our cells so that they will not be exposed to the immune system. Because one has to remember that diabetes type 1, the young patients, the children, have antibodies and T cells which attack their own pancreatic cells. So if you give them new insulin-producing cell, it will not help unless you can protect them from the immune system. Mm-hmm. So this still remains a challenge, but we are working on it in partnership with a French company, Australian company. we're just able to get big grants from the Innovation Center of the State of Israel and also from the European Union. So we hope to solve also the problem and be able to start clinical trial also in diabetes.
So it seems to me that we can maybe look at the 3 phases. The first phase was really that you studied how everything is sort of working together at the really beginning of the era of molecular biology. Then you switched to more arresting and stopping processes of immune disease. And now you're more into rejuvenation. As you age, you find your passion into trying to bring things back, build things all over again. So I would like to ask you, maybe from a more ethical point of view, are there risks in what science is trying to push forward in this field of research?
In the case of the embryonic stem cell, certainly we have challenges which are beyond the development of a normal drug. I mean, drugs made by chemists or drugs made by biotechnology using cells to produce protein, those don't pose very severe ethical question. But the very idea of taking cells from a blastocyst, that is, don't have to tell you, you are an expert, and you do that almost daily. You do the in vitro fertilization, and after 5 days you have the blastocyst and in cell mass. If you take this cell, the blastocyst will not be able to continue developing. So on the one hand, you have other possibility of this regenerative medicine, where you could make new organs. Maybe now we can make tissues, but maybe in the future we can make kidney, we can make organs that can be used for transplantation. And we can maybe even add cells which will keep people more healthy. So are we authorized to use an embryo and seize its existence in order to do that? And we had many debates. I was part of the UNESCO International Bioethics Committee since 1993 until about 2006.
How did that start?
About in 1993, the UNESCO decided that bioethics was very important. It was the start also of the human genome story. And one of the first declaration which we wrote together, 36 members of each one from another country. It's part only 1/3 of the countries which make, or much less even, because there are more than 200 countries. We wrote a universal declaration on the human genome and human rights, on all the problems of isolating genes, etc. But the problem of embryonic stem cell, which we started to talk about, was also very prominent in our debates, because many countries like Germany, Catholic countries, Eastern Europe, they did not allow to use embryos. But we knew that when you do the treatment, and actually you can explain it better than I could, that you are producing many embryos to help a couple who wants to bring
surplus embryos.
Surplus embryos, and once they have all the children that they wanted, you can ask the parents if they are ready to donate the surplus embryos that they are not going to use because they cannot give it to someone else, and the only thing is to keep it forever or to destroy it, if they are ready to give it for medical research. And in my mind, it is not very far from organ donation after death, because this embryo has no potential. If the parents don't want to use it, they have already their children. Maybe it's 10 years after the embryo has been made and it's frozen in one of your
liquid nitrogen tanks.
You can ask if they want to do a donation. And that actually was a line which we followed. Many countries adopted this line, and I'm glad that in Israel it was particularly active, and this line was adopted, that one can ask for a donation of surplus embryos. In the meantime, like science does, there was a big discovery of the potential of taking cells from the skin or other parts of the body, biopsy, and producing what are called induced pluripotent stem cells, IPS. It was a big discovery from in Japan, and it's now used very much in research. But these cells have problems because they are not completely normal. And they are also not yet completely safe because they undergo genetic modifications. So they are not normally natural stem cells like the one in the blastocyst. Mm-hmm. They have been induced by a process, a genetic manipulation, and they don't have the same stability. Probably this problem will be overcome, but there is still a need for the embryonic stem cell.
So you think in the future the use will be mostly from embryonic stem cells?
No, I think there will be countries that will not accept embryonic stem cell, and they will say we prefer to take the risk with the IPS. Maybe the problems of the IPS.
So it's not the science leading, it's the religion or the politics or
the ethics, yes. The ethics. Yeah. I think when you do science, any type of science, you have the choice of what are the means and the use of what you are doing. Take the nuclear energy, of course, can be used for peaceful means. Maybe ecologists today also think it's not very, very good, although there is still a big debate. But you can use it also for destructive bombs. And we know the world is still very threatened by this. So the scientists have to do a decision, and there was a famous meeting in Pugwash last century, and the whole ethical conditions in which you can do nuclear energy, atomic research have been set up, and scientists should not work on bombs, at least not the scientists who want to.
But they do.
They do. Of course, you cannot stop the military from bad application, but you at least stop those which are not, controlled by states, by rational states. We know today with Iran the problems we can have with North Korea when the states are not states on which you can rely. So they do, but I think the ethics has to be active. The public opinion has to be, and in general, I think today people understand the danger of nuclear weapons. For biology, maybe it's less clear. In human genome study, for example, all which has to do with making better humans, or quote unquote, that is to be to improve on nature, to make more intelligent, or make robots that will influence man, etc. All these raise very important ethical issues. Because if you decide that a human being is completely directed by his genome, and then you're actually reducing the human rights of that person. You can classify people which have a better genome than less good genome, so a racist approach. And this is all covered in this Universal Declaration on Human Genome and Human Rights, which wants to state that you cannot reduce an individual to his DNA. Human persons have history, they have environment, of course, education, beliefs, artistic gifts, and all this is part of their personality much more than the DNA. So all these ideas that I'm going to select the scientist is going to select the better genome, like in this famous film, Gattaca, where you see that from the beginning...
in Gattaca,
program.
it's a society where it's a film. Well, there's Andrew Nichols, and in this film, people are chosen based on their genes for a space project or something else, and very few people are. So, who do you trust in this duality? Do you trust the scientist? Do you trust the bioethicist? Do you trust maybe religion? Do you trust history?
I think what bioethics is trying to do is to integrate this different activity, because those are always multidisciplinary committees where you have scientists, you have philosophers, you have lawyers, very important, because everything has to be translated into law, and you have also religious people, or people who can bring their ideology and their ideas, and we try to work together and to come with some solution which is acceptable. That can be changed with time. For example, in Israel we had this big debate about sex selection during in vitro fertilization, and it is still not practiced, it is not permitted, but in certain special cases where really there is a real drama and a danger for the mental health of the parents or the mother, it can be permitted. So you are always trying to find the equilibrium, and you have to continue the discussion, continue the debate. For example, 20 years ago, I was active in the Knesset committees and prohibiting cloning and also genetic manipulation of embryos, so of reproductive cells, so that you cannot make changes in the DNA of a cell that is going to give a baby, although you can make change in a cell of a disease cell, like a blood cell or any other cells of the body, because you are then trying to treat one person. When you do something in the reproductive cells, you are doing something on an individual who is not yet born, and the condition in which he will live can be completely different from the conditions today. Now, there is a law in Israel which is re-examined every 5 years, prohibiting cloning, which could have some application, medical application, and prohibiting genetic manipulation of reproductive cells. But now we have this new technique called gene editing, in which it is very easy, CRISPR-Cas9, which allows you to make change, and they have already been made, in fertilized egg, human fertilized egg, where there is a mutation, you can correct the mutation, beautiful, you can make maybe a new human person instead of disease, you can cure his disease by repairing the DNA, the mutation of the DNA. So, should we change the law? Probably not, for the moment, because we know that this technique is not completely safe. You think you are repairing one point, but you can make change other points. In the DNA, in the genome is huge, 3 billion nucleotide. So I think it's not going to be tomorrow. But debate is going on, and we'll have to go on these questions.
I know from home that you are also a very learned man in the field of Jewish studies, in the Zohar, in Jewish maybe secrets. So has this influenced your work in any way, do you think?
Yeah, it has influenced my life, certainly. And from a young age, and inspired also by my uncle André Neher, we spoke about before, I was interested in this duality of science and religion. Try to keep them apart. I think one should do science without any input from beliefs or from... Actually, science has no finality. It has only causality. And you have to find the mechanism and try to use this mechanism as much as you can. But as we discussed bioethics, what to do with science is not a question scientists can resolve. It is a question that philosophers, people of religion, according to their belief, can actually decide what are the proper use of science. So although I've kept them separate, I've tried to occupy myself to study the Jewish thought and the Jewish Kabbalah, the Jewish mystical tradition. Why did he so? Because in Judaism you have, the halakha, the laws that you have to do to accomplish every day, put on talit or tefillin, to do things or give charity. But where is the philosophy? Where is the ideas behind? All of those have been in the mystical literature of Judaism. First of all, in the Midrash, in the many stories which are told in the about interpretation of the verses in the Torah. And then when the Zohar appeared in the 13th century, one got a completely new and different type of interpretation, not only of the meaning of the verse, but also its inner meaning. The words have several possibilities of interpretation, and this opens completely new horizons in understanding the Bible, in understanding the Torah. And I'm trying to learn that, to teach that, I've taught courses for over 30 years in Rehovot, and I'm trying to finish a book on commentaries on the Torah, on the weekly portion of the Torah, from a humanistic point of view, a point of view which is not contradicting science. For example, there is no contradiction between the sixth day of creation and the way we know the world, the universe exists for 40 billion years, because what the Torah is writing is not the description of the real world, but a description of our inner world, of our intellectual.
To me, it seems that you're dissecting the Kabbalah, the Zohar, in a scientific way.
It is true, because I'm not a man who believes. But I'm trying to understand religion more than believing in it. I'm doing the things which I'm requested to do, but I'm not, couldn't say that ani ma'amin, blindly. No, I'm not attracted by faith. I am more attracted by trying to understand in a certain rational way what is written in the Torah. And if you know, of course, of the 10 sfirot, the 10 spheres with which the Kabbalah is trying to summarize, the whole universe, the whole what exists, from the intellectual spheres to the most material spheres of the existence, and their interrelation is really rational, I believe.
So I think it was really a fascinating story, both from the family point of view and also from the scientific point of view, and the way of Jewish thinking. But what impressed me, I think, most is also chance. I mean, sometimes you meet people, Sometimes you decide that you want to go one way and things take you another way. But always there is a dream, always there is a purpose. And I think the fascination of really being your son and growing and learning to appreciate the communication between family life and the value of so many things that you do, and also always being curious about the next step and using these opportunities is really has been fascinating for myself and all the people that work with you. I know we recently celebrated right here at the Academy your 80th birthday. And unlike other celebrations that have to do with just mentioning the number of 80, I think it was really fascinating to see so many people from all parts that take in the creation of so many things that you did in the past, doing in the present, and hopefully for many years will do in the future. So we love you and appreciate you, and I thank you for this interview.
Yeah, I also want to thank you. I think you made a very good plan, and it's thrilling to be interviewed by one's son, older son, and you are a physician, you are treating people, you have this influence from my father who came down to you, and I think you're helping patients in addition to doing the research and being a director of department. And I appreciate very much the time that you have taken. I want also to say to the Academy of Science and Humanities, because actually we are in the Academy of Science, Israeli Academy of Science and Humanities. So also, I would like sometimes to be on the humanities side. I want to thank and to say how nice it is that the Academy is continuing the work on bioethics. We have a committee on bioethics at the Academy, and Meni is coordinating this committee. Dr. Meni Kirma is helping us a lot, and I want to thank this opportunity of going over my life, both on the scientific side, family side, and to say that I'm very happy that your children and my grandchildren are in many ways continuing the science. Many of them are studying physics or medicine and marrying students who are studying medicine. So there is a future, hopefully. And again, thank you very much.